So what you guys should be able to see here is something called message ID on top. So where we ended the last time session was we were talking about proof of work as a concept, not in relation to Bitcoin specifically, but generally what was created. And as we discussed, it was created to stop email spam. So now suppose we implement that kind of proof of work in an email system. What would it actually look like? So when we look at the header of any email, so for example, I'm using the Gmail interface. So it shows us that right on top there is a message ID. Then it says, okay, created at, from, to, subject. This information is here. Then we can see that Google does various kinds of checking. Like there is something called SPF, Sender Policy Framework, and DKIM, which is Domain Key Internet Management. So these are various kinds of tests that are run to make sure that the email is not fake, forged, that kind of stuff. So as we can see here for SPF, it says pass with this IP address. DKIM again pass with a particular domain that, okay, they've sent the email. Now, we could similarly, theoretically add something like POW here, which could be proof of work. And then it could say, okay, passed with a particular number as the nonce. And at the back end, what's really happening is this entire message ID, when that is concatenated with the sender and receiver's email address and the timestamp of when the email is sent, and we put the nonce here, 89804. If that entire thing is hashed, then we see that the hash begins with 4 zeros. So this is a theoretical example about how we could implement proof of work in an email system. Any questions? Is it clear to everyone what I'm trying to speak here? Can someone just quickly give me a yes, no, clear, something like that? Awesome. Great. So now let's move forward and let's see how is it that this proof of work concept is now implemented into a blockchain. Very similar to how Bitcoin has implemented it, but I'm explaining it to you, so I've kind of made things a little simpler. So let's say, as we know, every blockchain starts with block number 0. And then it goes on 1, 2, 3, 4. So let's presume that the blockchain we are talking about is actually on block 18. Now, how would the block headers really look? So theoretically, this is what's really happening. That when we look at block number 17, the block that came before it is block 16. The header of it contains 4 things. Previous hash, that's the hash of the 15th block. The timestamp, the transaction route, I'm going to show you how that's calculated, and the nonce. When these 4 things are hashed, they could go into the next block's header as a previous hash. Then this is the timestamp of block 17. This is the nonce of block 17, and this is the transaction route. So as you recall, I think we talked about Merkle trees last time. I'll just give you a quick overview. So suppose there are 4 transactions that happened in block 17 during a particular 10-minute period, let's say. Now each of those transactions, we calculate the hash. So because there are 4 transactions, we get 4 hashes. Then we take hash 1 and hash 2, join it or concatenate, rehash. And we keep doing this process till we are left with only one single hash. And that hash represents the 4 transactions. So similarly, there could be 10,000 transactions, but we reduce it to one single hash. We can call it the Merkle root. And this whole thing is called a Merkle tree. And these are the 4 most important items that would go into the header of a particular block. And then, of course, in the block would be actually the transaction information. And then again, we go to block 18, the same thing would happen. This block 17's 4 fields, hash put in here, and then block 18 begins its journey. So as we can see from all this, a blockchain is an ordered and time-stamped record, which means every transaction gets a timestamp. Every block gets a timestamp, and there is an order in which it has to go. So it is going 16, 17, 18, and it understands which is the block before it because it has a hash. And if somebody was to try to alter this data, block 17 would immediately realize that something is wrong. So that the blockchain would be able to detect that there is some kind of an attack or some kind of a fake entry which is happening. And that is why we say a blockchain prevents double spending. So as you may recall, double spending was the same token cannot be spent twice. Okay, so that is called double spending. So we realize that when it comes to currency, right? Currency cannot be spent twice because once we give the note, nobody else can spend that same note except the person who's now got it. So similarly, because of this whole way in which a blockchain is structured, double spending of these kind of electronic coins is also prevented. And finally, blockchain prevents modification of the previous records. So if you really want to make a change in block 17, you would have to make a change in all the blocks that came before it and then put the data into block 18. I hope that's clear. Any questions? If you have questions, just type them in. If you don't have a question, just say all clear and I'll move to the next one. Quick yes, no? Awesome. Now let's go on to the Bitcoin white paper again and see what is it that they talk about proof of work, right? So what they're talking about here, let me reduce the, okay. The proof of work, so now I'm only reading out the green part. The proof of work involves scanning for a value that when hashed, such as with SHA-256, the hash begins with a number of zeros. So that I've already shown it to you. You know, we are looking at 4 zeros as an example. Now we'll see in Bitcoin's case what really happens. It's much more than 4 and why. And then we can also see that we increment a nonce. Again, you've understood nonce starts with 0, goes to 1, 2, 3. We increment a nonce in the block until a value is found that gives the block's hash with the required number of zeros at the beginning. And the block cannot be changed without redoing the work. So like I said, if you want to make changes in block 18, you will have to repeat for so many other blocks. So as later blocks are chained one after the other, the work to change the block would include redoing all the blocks that are coming. So that is the reason it becomes very difficult for people to change the data. Somebody's asked about the 51% attack. Yeah, sure. We are going to come to 51% in a few more slides. That's covered towards the end. So transaction root. Yeah, Anupama, I'll briefly tell you. So transaction root is what? So let's say that we had 4 transactions in our block. So each transaction would say, okay, sender's address, receiver's address, amount, and other things. Now that data is hashed. So suppose there are 4 transactions, we have 4 hashes. Then these are the 4 ones. Then we take hash 1 and hash 2, join it, and this level hash comes. Then we take a transaction 3 and 4, the hash of that, join it and get this one. Then we join these 2 and get this one. So depending on the number of transactions, it would be that many levels. And finally, we are left with one single hash, which we call as the Merkle root. And the whole thing is called the Merkle tree. Are the nonces calculated for each block incremental? Like, I mean, the nonce for 17 was, no. There's no correlation. So every time that we calculate a nonce, it's a different entry input. So there is no way to predict whether a particular one takes more time or less time. So that's why it's it's not possible to predict how long does a block take. On an average 10 minutes, but it could be 20 in some cases, could be 45, could be 2 minutes. So no way to predict. Now here, there's another point. Let's look at the green part again. To compensate for increasing hardware speed and varying interest in running nodes over time. That means the Bitcoin white paper is written in 2009. Now, every year hardware speeds are going up. Then nobody knew at the time when the white paper was created how many people would want to run nodes. So the interest of people may change. When Bitcoin rates goes up, more people want to mine. When it goes down, less people want to go mining. So that is why it says the proof of work difficulty is determined by a moving average, targeting an average number of blocks per hour. If they are generated too fast, the difficulty increases. And obviously, if they're generated too slow, the difficulty decreases. So now we know on an average, it is supposed to be 1 block per 10 minutes. And depending upon the hashing power, the difficulty can be increased or decreased by the technology, by the system. And now I'm going to go deeper into the concept of difficulty. I hope everything's clear so far. I hope all of you can see the word difficulty written in the slide, which is now open. Just a quick yes would help me. So yeah, awesome. Now let's try to understand the meaning of difficulty, right? Now this is a slightly difficult concept as the name suggests. Let's make it simple. How many times more difficult is it to mine a block now as compared to how difficult it was to mine the Genesis block? Now let me first ask you a question. Which do you think is easier to mine? The first block of Bitcoin, which was done way back, say 2009, or today? Which is more difficult? Keshav says the first one was more difficult. Would anyone? Yeah, today. Okay, Keshav, you changed your answer on that, but you're right. Today is more difficult. Why? Because we actually have so many people competing. At that time, it logically would have been easier because it was just the creator. And I think in the first block, there was no transaction other than the 50 Bitcoin given as a block reward. Other than that, there was nothing. So we just had this first transaction. We also call it the Coinbase transaction. So if many of you are wondering why the exchange is called Coinbase, actually Coinbase is the first transaction of any block. And that is what contains the amount given to the miner as a block record. That becomes the first transaction of every block and it is called the Coinbase. Now, difficulty measures how difficult it is to find a hash below a given target. And what is target? Target is a number that the block hash must be below for the block to be added on the blockchain. Let me show you what it is. For that, let's do a quick recall. I think we've discussed hexadecimal before. If not, let's just briefly say it again. Nitin, about your why is it called Coinbase? Well, I think that was just a term which the founder came up with. I don't think there is a particular logic for why they chose that. Now, as human beings, we usually use the decimal system, right? So in the decimal system, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is simple. 10 is written like this, 11 like this, and we go on, and we know how to do our counting. Now in computers, there are different systems used. One is one is binary 0, 1, and one is hexadecimal. That's what we are going to talk about today. In hexadecimal, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is written as A, 11 as B, 12 as C, 13 as D, 14 as E, and 15 as F. So a lot of you know that my hacker handle always was D. Reason being, in hexadecimal, D stands for 13. And 13 is, I love the number and most people hate the number 13. So that's my favorite number. And because in hexadecimal it's D, so that was my handle. So it's as simple as that. Hexadecimal is a way of writing numbers where instead of going 0 to 9, we go 0 to 15 in this particular manner, right? Any questions on this? There's a question about if it means that the headers of each block contain the hash of the Merkle root and the details of the transactions that led to this Merkle root are in the body of the block. Yeah, so the Merkle root is in the header, but don't worry, I'm going deeper into it later. I'll show you what the block and block header looks like. We'll come back to that, don't worry. Now, and by the way, I would always recommend you guys to come and attend these sessions on Creator because then you're earning learn tokens. So as you watch more of the stream, you're getting learn tokens, but unfortunately you won't get that if you're on any other platform. So next time it'll be great if you are all on Creator itself. So is this part clear about what hexadecimal means? A quick yes would help me. All clear? Awesome. Now let's look at the number 500. So if we were to write 500 in hexadecimal, it's 1F4. Now it doesn't matter whether we use capital or small letters. Then 1000, and like this numbers are growing and we are writing it. So now you'll realize that when you look at a hash function, the result of a hash function, it is always alphanumeric because it is like this. So let's see now what it looks like. So now this is, I think, as of today, if I'm not mistaken, or maybe the last week's data. The current difficulty target of Bitcoin is this, right? So we can see there are a certain number of zeros here. Now, when we change this, now this is a hash. When we change this into decimal, it becomes like this. So now you realize that every time when the Bitcoin difficulty level is being changed, and it is changed, if I'm not mistaken, every 2016 blocks, which averages every 2 weeks. So every time that happens, the target is changed. It is made more difficult or easy depending upon what was the average block time. Now, right now, if this is the target, if you want to hash a block today, this one fits because as you can see, this number is smaller than this number. So forget the hash for now, just look at the decimals. So if this is the difficulty level and today we have just made a block, this is the hash of the block, it is accepted or correct because as you can see, this number is smaller than this number. So the system will not accept a nonce if the hash is not below the current difficulty level. And this target changes every, like I said, 2016 blocks. average 2 weeks. And that is why we say that blocks are mined every 10 minutes on average. Again, these are random numbers. The founder of Bitcoin set these numbers. There's no logic. I mean, he could have said instead of 2016, 5032 for all he cares. He could have said instead of 10 minutes, 4 minutes. His call. So if you look at, I think, Litecoin, it is 4 times. So everything in Litecoin is a multiple or a divisor of 4. So there, I think blocks are mined every 2.5 minutes. So they've just gone with that. Again, when you start your own blockchain, you can do all this, whatever you want. Yep. Somebody from LinkedIn liked it. Thank you so much. Any questions so far on the difficulty concept? Is it now clear? So now don't get confused when anyone ever talks about difficulty. A quick yes would help me. It's all clear? Awesome. And a higher difficulty implies a lower target value. So as the number of zeros increase, it becomes more and more difficult for you to generate the correct hashes. So the target value is lower. Now let's go back to the Bitcoin white paper. Now let's go to the section there which they talk about network. So always remember, in the world of blockchain, when we use the word network, why do we say network and why don't we call it a blockchain? So there are lots of confusing terms here. So ideally, when we talk about the software or the fact that it is running and all the ledger are in one place, the ledger of all the transactions is what we usually call the blockchain. And the network of all the nodes in the world, we just use the word network, right? Because nodes are all computers. It could be a single laptop, could be a server, could be anything. All of them are connected to each other. So we call that a network. So the Bitcoin white paper says that how is the network going to run? So step 1, new transactions are broadcast to all the nodes. Then step 2, each node collects these new transactions into a block. Then each node works on finding a difficult proof of work for this particular block. When a node finds a proof of work, it broadcasts the block to all the nodes. So it tells everyone, look, I found the answer. This is the data, this is the answer, this is the nonce. Now, nodes only accept a block if all the transactions in it are valid and not already spent. So they're checking for double spending. They're checking that all the transactions are valid. They've been digitally signed by the correct entity. Then nodes, point number 6 is very important. How does a node express the acceptance that yes, I have accepted the block? They do it by working on the next block. So 10 people have broadcasted. I picked up one, whichever came to me first, checked that everything was okay, and I immediately used that as the base to now calculate the next block. And that is the way in which a node says, okay, I have accepted. And now it always says that nodes consider the longest chain to be the correct one. So, as we know, every time this is happening, multiple blockchains get created, and every few blocks later, everyone checks to see, oh, there are so many. The system deletes all of them and only the longest one remains. So whenever I am accepting a block, I always make sure as a node, it is from the longest chain. Because at any given point of time, there are multiple chains running. We keep picking from the longest, and then in due time, the shorter chains get deleted. And those transactions are then rejected. In fact, when that happens in the Ethereum world, then we use a concept called uncle blocks. Yeah, UNCLE, the word uncle. I don't know why they chose it, but it's called an uncle block. But we'll go into that detail when we go into Ethereum. All clear? Any questions? Yeah, 6th point, sure. So as a node, so let's say I am a node, you are all of us attending this lecture, there are 57 of us right now. All 57 of us are running nodes. Now, suddenly someone has broadcast the nodes to us, and we find 5-6 different nodes have been broadcast. So we will try to see at that time which is the longest chain, and we will accept the node or the block given by the longest chain. So there's somebody who's got 8 blocks, somebody who's got 9, we will choose the one with the 9. So at every given point of time, we always look at the longest chain. Hope that's clear. Okay. Then another very important thing, does node get transactions in a particular order? No, not really. So what happens is, all this goes into the memory pool. There's no particular order. And secondly, as the miner, you can choose to neglect some transactions. You can say, you know what, this transaction is giving me 0 fees, or it is giving me low fees, and I can reject it. And I will only take, logically, as a miner, I will take only the ones which give me the most fee. Then comes a time when I feel, okay, you know what, there are not too many transactions. So I take even the free ones, which is why, remember, on the blockchain, in proof of work, transaction fee is optional. It is not mandatory. You actually can set the fee. So if any of you have used MetaMask to make a transaction, I'll show it to you maybe next or next to next lecture. We can actually speed up our transaction by paying more fees. So when a MetaMask transaction begins, it actually shows us that, you know, okay, it's going. Do you want to speed it up? I can click a button, pay more transaction fee, and then it can go faster. So we'll see a practical application of that soon. What if the one with the longest chain is a corrupt one? Yeah, Nitin, that's a very good question, and I'm going to come to it very soon. I'm going to show you how it happens. How does a node, when there is a transaction occurred, does some pop up similar to OTP? No. So what happens is, here we have a concept called a memory pool or a mempool, and maybe, you know, one of the good ways to see it, you could just set up your own Bitcoin node. It's very easy to do. And in that, you'll be able to see how the mempool gets populated. But don't worry, we are going to have a session later where we are going to set up our own blockchain. So there we are going to actually view the mempool in real time. So we'll come to that, don't worry. Then we talk about incentives. So we're going back to the Bitcoin white paper. And it says that by convention, the first transaction in a block is a special transaction that starts a new coin owned by the creator. So you remember I told you that is actually the new coins generated and given to the successful miner. That becomes transaction one. This adds an incentive for nodes to support the network, and of course provides a way to initially distribute coins into circulation, because on day one there were 0 coins in Bitcoin. How will new coins get created? So the system works in such a way that every block creates new Bitcoins. Now the number changes, right? So initially for the first 4 years, now again I'm saying years, but it is a number of blocks, 50 Bitcoins were given per block. After that, the first halving occurred, half. So it became 25. Now, then it became 12 and a half. Today, it is 6.25. So today, every block which is mined gives 6.25 new Bitcoins. This number will keep becoming half till approximately the year 2140 AD, 100 years to go. That time, all the 21 million Bitcoins would have been generated. No new Bitcoin would happen because that number would have fallen, becoming half of half, it would go to 0. And then only transaction fees would be the revenue model. No new coins would come into the picture. And why are we giving the miners? Because miners are spending CPU time and electricity. So that is the reason they are getting these rewards, and they are getting transaction fees. And because in Bitcoin there is a fixed number of coins, 21 million total, and we know the rate at which they are being issued. So we say Bitcoin is free of inflation. Well, not really free of inflation, but yes, inflation is very low because we know it. So ideally, inflation means no new coins are created, right? But government can print as much money. That is why inflation keeps changing. In Bitcoin, because we know the number of coins, so the inflation is actually extremely low. Someone has asked on LinkedIn, what happens when there is a new one getting added after considering the longest, a new transaction? Don't worry, I'm going to come to this in detail, and you're going to learn something really, really interesting. Is Bitcoin more like a loyalty recognition token? No. So you get Bitcoin for mining blocks, and every one block there is going to be a fixed number of things given out. In some ways you can say, yeah, okay, it's loyalty also. So in return for mining, you're getting paid. But see, in a loyalty system, what happens is everybody who spends money gets loyalty token. Like Learn, everybody who attends earns it. But in Bitcoin, hundreds of miners are there, but only one guy finally wins. So in that way, it's not really a loyalty token. If I'm running a node and I mint a block, will I get 6.5 Bitcoins? Yes, you will get 6.5. No, 6.25. So 50, 25, 12.5, now it is 6.25. So today, if you mine a block, you get 6.25 currently. Yeah. How about one node malfunctions? Doesn't matter. That's the beauty. That's why we say blockchains do not have a single point of failure. There are supposed to be many nodes. That's why we say it's decentralized, which is why when a blockchain like Solana goes down, it makes no sense, because it means every single Solana node went down at the same time. How is it possible? Which means it is not decentralized. It is one organization running all the nodes. That's why all of them went down at the same time. That's never happened to Bitcoin because there are so many people around the world, including people like me, who run nodes. I, in my entire life, may not have mined a node in the last few years. I've not mined a single block, but I keep doing it because that's my contribution to the system. So as long as there is even one node running, Bitcoin doesn't go down. Transaction fee is added. Yes, you're right. So not only do you get the 6.25 Bitcoin, you also get the transaction fee of all the transactions that took place in that block. Does it mean 51% of the nodes failed or the entire? No, no, no. When a blockchain goes down, Tarun, it means every node went down. Even if one node was running, the blockchain should have been running. So in Solana's case, I'm very shocked why that really happened, which obviously means it's not decentralized. Let's go to another one. They say that in the Bitcoin white paper, the incentive may help to encourage nodes to stay honest. So the logic here is, if you're a Bitcoin miner and you're spending all this electricity and you get paid by way of transaction fee and new, it is in your interest not to mess with the system, because if you break the system, people lose trust in it. The value of Bitcoin goes down to zero. You as a miner will lose your money. So it kind of encourages you not to mess around with the system and to remain honest, unless by being dishonest you end up making more money. So it's ultimately pure and simple about incentives here, economic incentives. Where does these Bitcoins and transaction fee get? Yeah, it's a wallet. Yes, you create your own. So miners have addresses and it goes to that address. It is not decentralized enough. Yeah, so in Solana's case, yeah, obviously I'd say it's not decentralized enough. Why transaction fee when new coins are making for now? So see, if there is no transaction fee, what could happen is people, to overwhelm the system, could make millions of transactions of tiny amounts of money. So when you put a transaction fee, you're making it expensive to broadcast a transaction, and that's the reason transaction fee is used in a proof of work system, to reduce the flood of transactions. Otherwise, a denial of service attack becomes very easy. So I hope, Harshil, that's clear. Let me go to the next one. Now, we spoke about Merkle trees. Why are they used? Obviously, the reason is pretty simple: to reclaim disk space. So, we don't want that, because if there are 10,000 transactions and we store 10,000 hashes in the header, it becomes too much. So that's why we only put one, and that's why the concept of Merkle tree comes in, which I've already explained to you. So this was the Merkle tree. And here I've given an example that, every transaction is digitally signed by the sender's private key. And theoretically, it could contain this sender's address, which could look like this, receiver's address. Now I'm showing you of another blockchain, not Bitcoin, but a blockchain where multiple coins are there. So we say, okay, which coin are we talking about and what is the quantity? So when we create our own blockchain, we are going to create a blockchain like this, where we can create multiple coins, similar to what Ethereum does. So this is the kind of information in every transaction. This is how it's getting hashed, concatenated, till finally we have one single thing left. This entire tree is called a Merkle tree, and the final hash is called the Merkle root. Hope that's clear. Okay. Now let's go to the next one. Now this is something very interesting, that when we look at Bitcoin, so we say that a user only needs to keep a copy of the block headers of the longest proof of work chain. So as we know, multiple chains are being formed at any point of time. As a user, or rather as someone running the node, you would only keep the longest proof of work chain. Simple to understand. Now let's continue reading the white paper, and if you have questions, please keep putting it. What if odd number of transactions? Yeah, so in that case, let's say there was only one transaction, then the hash of that transaction is recalculated and the both hashes are concatenated and done. So you just duplicate the last transaction if it is an odd number. Yeah, that's an interesting question, Sana. Now, continuing the white paper, the verification is reliable. Now here the important part begins. The verification is reliable as long as honest nodes control the network, but more vulnerable if the network is overpowered by an attacker. So now we can come back to that 51% attack question. Then what happens if more than 50% of the nodes become dishonest and they try to flood false transactions. We'll see how that happens. So it is always recommended that any business that receives frequent payments should run its own nodes for more independent security and quicker verification. So it is always recommended that you run your own Bitcoin nodes if you are doing a large number of transactions. So logically, a lot of people should be running nodes. We will come back a little more again to this 51%. In the meanwhile, now let's talk about a very interesting concept called UTXO. What is the minimum number of transactions that need to be present for a block? No, even zero. So if there are no transactions that happen, but there is always going to be a new coin creation transaction called Coinbase. So that one single transaction is enough. In fact, if you look at Bitcoin, if we look at the Explorer, the first, I think hundreds of transactions were just Coinbase. There were no actual one-to-one transactions happening. Someone's question is there a centralized exchange as a redundancy limit to store reference to the longest chain? So yeah, centralized exchange logically should be running their own nodes, but I don't know if they actually do or don't. Good question. Now, one thing you've got to understand, where Bitcoin is a little different. See, when you go to a shop and you make a payment using a debit card or a credit card, suppose you want to pay 103 rupees, dollars, whatever, you pay exactly 103. Do you pay 200 and then they return, say, 97 to you? No, right? You're only paying the exact amount. Am I right on that? When you use a credit or a debit card, you're paying the exact amount. But when you pay in cash, right? Suppose you want to pay 97 and you have a 100 rupee note. So you pay 100, the vendor deducts 97 and returns the 3 to you. So I put that in the chat. So in cash, it is always you pay more unless you have the exact change and they give you change back. That is how Bitcoin works. So this is quite counterintuitive and most of you may not have realized this. That in the world of Bitcoin, when you make a payment, it is never identical. It is never exact, right? You will pay a bigger amount and then you will actually get back some change in an address which is ideally supposed to be new. So how they've explained it in the white paper is that to allow value to be split and combined, transactions contain multiple inputs and outputs, right? So what happens is, as you're making more and more transactions, the number of addresses in your wallet are supposed to increase. And with every transaction, change is coming back to you, adding more and more. And now when you want to make a payment, multiple transactions, multiple addresses contribute Bitcoin to make a payment. Now, on the face of it, this sounds very illogical, but actually it makes Bitcoin really fast. This concept is called UTXO. So in the world of blockchain, there are three, actually I mentioned two here. There's a hybrid model also, which I think blockchains like Cardano use. There are two main types of record keeping. One is UTXO, which is unspent transaction output model. This is used by Bitcoin, Bitcoin Cash, those kind of blockchain. And then Ethereum uses something called account balance. So each Bitcoin transaction spends output from prior transactions. Each Bitcoin transaction also generates new outputs that can be spent in future. And when you look at your wallet, although it shows you the overall balance, it actually keeps a track of all the unspent transactions associated with all addresses owned by you. So as a Bitcoin user, you may have hundreds of addresses. Your wallet calculates the total and shows you, but it is not all in one address. It is spread across multiple addresses, and when you make a payment, it combines them, makes a payment, receives the change back. So Bitcoin transactions are like currency notes. Ethereum transactions are like credit cards. I hope that part was simple. Any question? Yeah, I understand it's a little complex, but don't worry. What I would recommend, look at this video again after we are done. Look at the YouTube recording. Trust me, you'll understand. Yeah, because right now I want to quickly finish some more topics, so I won't be able to repeat that. But look at it again, and if you have a problem in the next query resolution session, I'll handle it. So the balance of a Bitcoin wallet is the sum of all those unspent transactions. And like I said, UTXO is like spending banknotes and getting back change. And the benefits are scalability and privacy. So privacy is only there that if you use new addresses for each transaction, and that is recommended in the white paper, every time you make a transaction, use a new address. So then it becomes, gives you privacy because then nobody can trace who the person is doing these transactions. Then this is a diagram. I mean, it's okay. It looks a little complicated, but it kind of explains the same thing. That as inputs are coming in and outputs are going, this is how it actually grows. So it's a fan out kind of a model. More and more transactions you make, more and more addresses coming, and that's how the input output keeps happening. But don't worry, it's a little complicated, and that is why we say in Bitcoin it uses something called triple entry. So if you're from a finance background, you know that we use double entry accounting. In blockchains, it's triple entry because of the UTXO kind of a model. So as we said in privacy, that privacy can be maintained. So if you can see the green part, by breaking the flow of information and by keeping public keys anonymous. So it's kind of like when the stock exchange gives information about transactions. It doesn't tell you who did what. It just gives you overall. So Bitcoin also shows you the overall transactions and it only shows you addresses. But who is behind the address is not known. So when you do a transaction with someone, you come to know, okay, this is the guy behind this address. And then slowly, slowly we can piece it together and figure out what all that person did. Someone's asked that if we pay more money, then who will send the money back? It's handled by the blockchain. So when you make a payment saying, I want to pay, say 0.8, it sends 1 and gets 0.2 back. You don't have to manually do anything. It's all taken care of by the blockchain because you've signed only for 0.8, but it's giving out 1. So it brings back. So all that is done, taken care of by the technology. Will MetaMask make a ledger of the return cash? So MetaMask doesn't do this because MetaMask doesn't support Bitcoin. It supports EVM blockchains. In EVM, this doesn't happen. So like I said, Ethereum and EVM blockchains don't use this, they use account balance. So there it's very simple. You want to make a payment, you will pay the exact amount. So that's like a credit card payment. That is why in MetaMask you will not see this. This will only happen in Bitcoin wallets. Hope that's simple, clear? And like I said, the white paper recommends that a new key pair should be used for each transaction. Then there are calculations which we are going to see. So the Bitcoin white paper tries to see a scenario where an attacker is trying to generate an alternate chain faster than the honest chain. Now here I have something quite controversial to explain to you. I don't know if I asked you this question, I think in the last session. Is it possible today for the entire Bitcoin ledger to be rewritten today? Right from 2009 till today, can we rewrite all the transactions with new ones? Is it possible? What do you guys think? Yeah, so Saurabh says yes. Okay, quite a few of you say yes. So actually you're right. And that's what now we are going to come to. See, always remember what Bitcoin uses is not really proof of work. It is called the Nakamoto consensus because it is a probability based proof of work. I showed you proof of work as originally created by, I forgot his name, Hashcash, I mean, John something, I've forgotten his name. When he created proof of work for the email thing, there was no probability in it. It was fixed. You have to calculate the nonce, story over. But when it was introduced into Bitcoin, it is probability based, saying that a node will always accept the longest chain. So it is theoretically possible today that somebody comes with an amazingly fast machine or finds out some kind of flaw in the code and creates a new series of blocks from block 0 till today and completely rewrites the chain. Now to do this or to prevent this, the Bitcoin creators did slightly something controversial where after every number of blocks, some data is hard coded into the software of the Bitcoin. The Bitcoin software actually hard codes it. So now you can't go back to the past and overwrite it. But the method is actually not right, and logically that's not how you should do. You should never be hard coding this kind of data into the software, but they've done that to prevent something happening like this in the future. Now I'm going to show you a little bit of probability. Now Tell me one thing, how many of you love mathematics from school, especially when we learned about probability? A quick yes, no. You like it or you don't like it? No, yes, okay. Okay, I can see it's 50-50, right? But unfortunately, you don't have a choice. I'm going to teach you something a little basic. So yeah, Viman says definitely no. Bear with me, it won't take much time. What does probability mean? Probability means what is the chance of something happening. So suppose I toss a coin. What is the probability it will be heads or the probability it will be tails? Can someone answer? What's the probability of it coming up heads? 0.5, absolutely correct. Now, the first time that I tossed it, it was heads. What is the probability that the second time I toss, it will be heads? Again, what? Absolutely correct. Again, 50%. So every time that you toss a coin, the probability remains 50-50 because there are only two options, heads or tails. Correct? Now that's the basic concept of it. Now in Bitcoin, let's look at what they're trying to see here. P is the probability that an honest node will find the next block. And Q is the probability that a dishonest guy, we'll call him the attacker, will find the next block. And QZ, so there's a small Z below it. You can see below this Q, I'll just increase it. Hope it's clear. So QZ, what is this? That is the probability that the attacker will catch up. So, I told you we're trying to figure out, we are already certain blocks ahead. The attacker is behind us, behind by Z number of blocks. So that number could be 0, 1, 2, 3, 4, anything. So what is the probability that this bad guy will catch up? So now there are two options. The first is the probability is 1 if P is less than or equal to Q. That means if the probability of the good guy finding the next block, which is P, is less than or equal to Q, which is the probability of the bad guy finding the next block, then 1, which means definitely the bad guy will catch up. Second, if P is greater than Q, that means the good guys are higher in terms of their hash rate. So the probability of them finding the block is more. Then the formula to calculate it is Q divided by P raised to Z, which is probability of bad guy divided by probability of good guy, raise that to the number of blocks by which the bad guy is behind you. Wasn't too difficult, right? Was it easy so far? Is that okay? Yes, no? Quickly give me a yes, no that this so far. Okay, awesome. Because now I'm going to make it a little more difficult. So P greater than Q is probability of the good guy is more than probability of the bad guy, right? What does that mean? That the good guy has more hashing power. That is where that 51% attack is coming into the picture. So when we are saying P and Q, if the good guys are having 51%, or rather it's not 51 actually, it's 50% plus one more unit. So let's say 51 for simplicity. If the good guys are 51, the bad guys are 49. They are less, so they will not be able to. It will become very difficult for them to have a catch up, right? Catch up behind means how many blocks behind are they? They are 3 blocks behind and they're trying to catch up with us. Because we are trying to see how many blocks are they trying to rewrite. Because maybe the bad guy made some payment 3 blocks ago and now he wants to cancel that payment. So he has to go and change the block which is 3 blocks ago. So we say he's 3 blocks behind us. He has to replace all the blocks which came after it. So he has to replace those Z or those 3 blocks. Now let's go slightly into the complicated part, which is, now I don't know, have you guys ever heard of Poisson distribution? This word here, Poisson distribution. Do any of you remember that? Oh, awesome. Some of you do remember that. That's amazing. So where we actually use Poisson kind of distribution is, so let's say that, someone is running a call center. And in the call center, they've calculated that on an average, every day, how many calls do we get? So now when they want to decide how many employees they are going to keep, they actually need to figure out the hourly probability that, okay, every hour it is probable there will be 3 calls coming. So then we will decide how many employees to keep. So that is where this whole Poisson distribution comes. You also use it when you're talking about the probability of a hurricane, tornado coming. That's where it all uses it. And there we use this symbol, and it is calculated as Z Q by P. So Z is the number of blocks, Q is the probability of the bad guy mining the next block, and P is the probability of the good guy. So this is the formula we use. And then if you guys remember this sigma, and do you remember studying limits in school where we did limit 0 to Z? A quick yes no if any of you remember that. Don't worry if you're not remembering it, just ignore this part, zone off. I'll tell you to zone back in after some time. So if you want to try this out, it's very simple. Do it on a piece of paper. My daughter did it. She's in 11th. She's done maths till 10th. So don't worry. Anybody who's done mathematics till 10th should be able to do this. Simple way to do it is presume that this Z is 1. Okay. And then the calculations are given here. So we will do summation of k equal to 0 to 1. So we will do this entire calculation which you see here. We will first do it for 0, then we will do it for 1. And here the numbers are simple. We calculated this weird looking symbol by using this formula. E is the Euler's constant which is known to us. We have this minus of that weird looking symbol. K is 0 or 1 when we do it for both cases. Factorial you may remember from school again. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 3 into 2 into 1. So that's simple calculation. So take a pen and paper and you can simply do this calculation. If you want, I'll just do it on a pen and paper and show it to you guys later. I'll put it up there. And Vishwadit, you're in high school. So if you're not in 10th, don't be scared. When you reach in 10th, you'll be able to figure out what this one is. Now, this is all from the Bitcoin white paper. So now what the guy has done, he said that looking at this formula, now he has given us some options. So suppose we say Q is 0.1. What is Q? Probability of the bad guy mining the next block. Now tell me, if Q is 0.1, what is P? Probability of the good guy. What is the answer to P? Can someone type it in? 0.9, absolutely correct. And why is that? Because total probability is 1. I mean, good guy does it or bad guy does it, total, somebody has to do it. So if good guy or bad guy is 0.1, good guy is 0.9. So when bad guy is 0.1, and how many blocks behind is the bad guy? 0 blocks, which means he's with you. Well, then he's definitely going to win. Probability of him winning is 1. But if he is 1 block behind you, probability now falls from 0 to 0.2. So it's a huge fall. Now, if he's 2 blocks behind, it becomes 0.05. Do you see how fast the probability has fallen? And now, as we go step by step, if the bad guy is 3 blocks behind, probability is 0.01, 0.03. And you remember I told you we always wait to 6 blocks. At the 6th block, the probability has now become 0.0002. So the probability of the bad guy catching up is now very less. And as the number of blocks increases, this probability becomes lesser and lesser. By the 10th block, we can see it is so low. But remember, this was for 0.1. What if it is 0.3? Then obviously things start to change. Then we see it becomes 0.1, 0.4. And again, it's happening, but here now he's presuming 5 blocks, 10 blocks, 15 blocks. So that is why Bitcoin mining is a probabilistic game. It is completely based on probability. Nobody can be 100% sure. We wait for 6 blocks, but again, there's no logic behind it. You could wait for 10 and still things could go wrong. It is possible somebody in the future may come and mess up the system big time, but well, that's a chance we take when we use Bitcoin. Now, this is a problem with the way in which proof of work is implemented in Bitcoin, because that is competitive proof of work. Later, I'm going to explain to you. So, for example, in my own project, we use something called as round robin proof of work. And I'll explain to you why that is much better, consumes much lesser electricity, and it is not based on probability. But don't worry, we'll come to that later. And then there are many other algorithms like proof of stake, proof of burn, proof of history, all have their own plus and minus. Personally, I still believe in proof of work, but not in the competitive proof of work, but in the round robin proof of work, which we'll come to later. Is this entire probability formula coded in the software? No. So the probability formula is only given in the white paper. In the software, it's just all the mathematical formula is integrated. The probability part is how reality works, because very difficult to know. And that is why if it's like we say, if the bad guys have 51%, they could end up ruining the system. Till today, it's not happened. We can always see what is the probability of bad guys getting enough hashing power. So there is a site called Nice Hash. You could go there and people can rent out hashing power there. So we can always see that how much percentage is available there. Till today, 51% has never been available there for sale because it's huge for Bitcoin. But for some of the smaller ones, like there's a Bitcoin blockchain called Bitcoin SV, Satoshi Value. No, Satoshi Vision. It's a fork of Bitcoin. Last year, it's thrice they have had a 51% successful attack. So there are many blockchains which have faced a successful 51% attack. Bitcoin till today hasn't. All clear? So I'm going to now quickly go to the conclusion. So in the conclusion, actually we can skip the conclusion. I want to show you a block. So when we look at a particular block like 746468, when we look at this block, in any explorer, we can see a lot of information. So we can see it was mined on 25th July at this time by a particular mining pool called Ant Pool. It has 430 confirmations, which means after this block, 430 more blocks have been mined. But this was when I took the screenshot, which was on July 25th. The miners of this block got 6.25 Bitcoin as a reward, and then they got 0.17 Bitcoin as a transaction fee. That's about $3,900. The block rewards, also known as the Coinbase reward, were sent to this address, so you can click and see their address also. So you could go to any explorer and it would show you all this data. For every block, we can see the hash, confirmations, which means how many blocks came after it, timestamp, height means the number from 0, what is the number of this particular block, the miner, the number of transactions, the difficulty level, the Merkle root, the software version, transaction volume of that block, 6.25 block reward, fee reward, all that is there. And then we can also see that a block header, you remember I told you I'll come back to this. So the block header contains all this information. So firstly, it shows you the version of the software. Whenever you update, new version comes, that's 4 bytes. We have the hash of the previous block, which is 256-bit hash, 32 bytes. Hash of the Merkle root, again 256 because we're using SHA, that version. So every time a new transaction comes, this hash changes. Every time a new block comes, this hash changes. Both are 32 bytes. Then time is the current block timestamp in number of seconds since 1st Jan 1970. So if you're a developer, you know that's called the Unix timestamp. So that is every few seconds it comes in, 4 bytes. Bits is the current target. I showed you what it looks like. Every time the difficulty is adjusted, that changes. So which is approximately every 2 weeks, which is 2016 blocks, again 4 bytes. And the nonce, which is a 32-bit number which starts at 0, 4 bytes. So this is the data which goes into the header. So every Bitcoin block has these 6 things in the header. Simple. If you transfer Bitcoin from MetaMask, no, you can't. Bitcoin cannot be stored in MetaMask. What you can do in MetaMask is called the wrapped Bitcoin, which is an ERC20. But you cannot put Bitcoin into MetaMask because MetaMask is for EVM compatible blockchains only. Right? This is block 0, the first Genesis block. So as we can see, there was no transaction fee. There was only a 50 Bitcoin reward, which went to the founder or the creator, who is known as unknown. Nobody knows who is. And there we can again see the hash of that block, confirmations after it, same data. 0 is the height because it was the first ever block. Number of transactions was 1, the Coinbase transaction. Merkle root, everything else is the same. Right? And this is the transaction in it. So we can see what were the addresses. It's as simple as that. And like I told you before, that from time to time one block becomes longer. Many blocks come and we delete and we only keep the longest block. So when a blockchain reorganizes itself, we call it a reorganize. So a blockchain reorganize happens when one chain becomes longer and the older chains are deleted because they are shorter, and all the transactions which are now rejected, they are called orphan blocks. In Ethereum, we call them uncle. Here we call them orphan blocks because they have no parent. They are not connected to the Genesis block, right? That's about it, I think. Yeah. So that's kind of about what I wanted to speak to you about the Bitcoin white paper. So this presentation is available to you. The recording of this one. So what happens to the orphan blocks? Well, they just lie around. So we deleted. They are not part of the valid blockchain because a block is considered valid only if it traces back. There's a single line joining it to the Genesis block. If not, we call it orphan, and those transactions, as you can see here, they become 0/unconfirmed. So that's kind of how the whole system takes place. So which blocks show these blocks data? So you can go to any blockchain explorer like blockchain.com and just Google blockchain explorer, and there are many of them giving you, right? So now I'm going to put this video up anyway, and then you can see your homework also. So just make sure that you keep checking the official LinkedIn group of the course. I'll put up the homework for the next one. And yes, this presentation is also there. All the links, everything is there. And this is the course page, if you guys can see it. Just give me a second. I will share it. Give me 1 second. So this is the course page. I'm going to put the URL in the chat for you guys. Right? You can see the course page, I hope. So the moment the lecture gets over, okay, I put the link here. So the moment the lecture gets over, I put the link here. So you can easily access it. And then certain topics like here. So I put it here also, right under the syllabus. So you can see white paper part 1, just click here to watch. And these are the carousel posts that I've already created and put it, and all the links are here. So in the homework, when I tell you to read something, I anyway give you the links, but all of it comes here. So just make sure you keep checking it. It's as simple as that. I hope it's all clear. Someone's asked, is cryptography knowledge mandatory for being a blockchain developer? No. A little bit of basics helps, but no, it doesn't matter. If you don't know it, it's fine. Okay, so it was great speaking to all of you. And for those of you who want to listen to the Hindi version, the creator team has put the link. It's going to start in 2 minutes. So at 8 o'clock, we start with the Hindi version of the same lecture. Feel free to attend it if you want. See you guys. Check your homework. And I will see you next Monday at the same time. Bye-bye.